the seminar formally. Welcome, everyone, and we are very happy and very excited uh, to see Professor Micheal Joswig, who accepted our invitation for this John Conway Spated Seminar Series. So, Professor Joswig is currently affiliated with TU at Berlin, Technical University in English, I would say, and he's an Einstein professor for discrete math and geometry there since 2013. His mathematical interests include geometric combinatorial, discrete differential geometry, combinatorial topology, discrete optimization, mathematical software, and related areas. And earlier in 2006, he was a research professor, also associated with University of California, Berkeley, USA, and he's also interested in polyhedral theory, and recently tropical geometry is in the fashion, and many aspects of tropical geometry evolved on the boundaries of these areas. So he's going to talk about tropical geometry and algorithm in geometry today as well. And so it that these kind of topic also involve definitely touch almost all the areas he's already working at. And welcome once again, Professor Micheal Joswig, in our seminar. I didn't mention your MPI, Max Planck Institute Association, as well. So this is something, a new development, or anyway.
So this is now for 3 years. So it's a temporary position as a Max Planck Fellow. It's a 5-year position, and I'm into my 3rd year.
And probably this tropical geometry is the result of that particular status of MPI, or you started earlier?
No, so that was a little bit. That's a very long story. So that started in Paris in, I think, 2012, and then it took a while to develop. And but yes, in Leipzig, I'm interacting with Bernd Sturmfels on tropical geometry related topics.
Yeah, very welcome in our John Conway series. Over to you, Micheal.
Thank you very much for the kind invitation and the friendly introduction. So I'm sorry that I cannot be with you personally, but it's a great honor to speak in your seminar series. I hope you can hear me. Yeah, so I'm a great admirer of John Conway's work, and I hope that I can deliver a presentation which is yeah, worth enough to be connected with his name. All right. So I want to talk about one specific result that I obtained jointly with Xavier Alamijon, Pascal Benchimol, and Stéphane Gobert a while ago. And let me start with this result right away. And then, of course, the talk will be about explaining the various parts and giving more details and explaining a little bit of why. So the result says the following. There's a family of linear programs such that a large class of interior point algorithms takes exponential time to optimize. So that family depends on a parameter, and it means the running time for these optimization algorithms is exponential in that parameter. And of course, I'm assuming that maybe not everybody is familiar with linear programming and the various algorithms and their running times. So then please note the word tropical geometry occurred in the title of my talk, but it does not occur in the statement. And that is actually part of the message already. Okay, so that is just a teaser. So this is what this talk is about. And let me go to the details. So there's a field in mathematics, tropical geometry, which has received some attention lately. And so it sits in between algebraic geometry, polyhedral geometry, and optimization. And I will focus a little on the connection to optimization in particular. I will give you a little bit of a glimpse of a summary before I go to the main part of this talk, which is about linear programming. So linear programming is an important problem in optimization that is relevant both for theoretical and practical purposes. There are various standard methods known. All of them are applied both theoretically and practically. And so there were open questions, and there still are, and I would like to explain, give you some answers to some of these questions which were open previously. And of course, the talk should connect all of that. All right. So let's start with tropical geometry and why it is related to optimization. So everything started with creating a new arithmetic on our favorite set of numbers, maybe the real numbers. So in high school, we add and multiply these and sometimes divide and so on and so forth. But so now we do this in a slightly different way. So we create a new addition, which is just the ordinary maximum of two real numbers. And we take a new multiplication, which is the former addition. And if we use this particular addition and this particular multiplication, we get the structure of the C-mi ring. And so what's the most important thing about a C-mi ring? Well, so you have the distributive laws, and here you see one example. So 3 plus 5 in this new arithmetic times 2 is 5 plus 2, and that is 7. And so that is the same as taking the maximum of 5 and 7, which is 3 times 2 in this new arithmetic plus in this new arithmetic 5 times 2. All right, so this is just a very easy definition of an arithmetic structure, which at first sight looks very weak. So there's no subtraction here in this, so therefore there's no field structure or not even a ring structure underlying, only a C-mi ring. Nonetheless, so this topic has been discussed in the mathematics and computer science literature since the 1960s, maybe before. There's a number of interesting texts which have been written since then, including an early monograph by Cunningham Green. And it was related to optimization, functional analysis, signal processing, and a number of other things. So what I'm referring to when I talk about tropical geometry is towards the more modern development, which made the connection to algebraic geometry, and the names to mention are Kapranov, Michalkin, Sturmfels, Viro, and many others. All right, so how does this work? So sometimes if you hear about tropical geometry, people say, well, tropical geometry is the piecewise linear shadow of a classical algebraic variety. So, and this picture is meant to explain how this is supposed to work. And what you see here is a polynomial in the lower part. So it's a three-variate polynomial in the three variables x, y, and z, which depends on an additional parameter t. And so just think of t to be some sufficiently large real number. So let's say 16, okay? So assume that t is 16, and then you have a polynomial in three variables x, y, and z. You can look at the degrees. You will see it's a homogeneous degree for a polynomial. And so then algebraic geometry is concerned with solution sets of polynomials. And if you are interested in the solution set of this one polynomial, so you set it to 0 and you ask for all the points x, y, z in homogeneous coordinates. So you're working in the projective plane, let's say over the complex numbers. And then you're looking at the vanishing locus of this one polynomial. So then this describes an elliptic curve. So as it happens, it happens to be a smooth elliptic curve. And so then, because it's a plane curve over the complex numbers, which means it is a complex variety of one dimension, which means it is a two-dimensional real variety. So, and just because of the complex structure, it is so then you have a two-dimensional differentiable manifold, which is orientable. And so in this particular case, so that oriented surface looks like this this yellow shape on the right hand side. So it's a genus 3 surface, oriented surface. So this is one way of describing this object. And I already told you it is smooth, and this is what you can see from the picture. Of course, so this is the yellow picture is just a smooth topological picture, so there are no correct coordinates or something. So what you see on the left-hand side, so that is that tropicalization. So it's a tropical variety. So there's a process to go from the algebraic equation to something else that gives you something which is piecewise linear. It looks, in this particular case, like you see on the left-hand side. So it is again a planar picture. So we took 3 homogeneous coordinates. So this is something which lives in the plane. So this was a plane curve. And whatever we did to this, we transformed into something which also lives in the plane. But now it lives in the real plane. And it is piecewise linear. And the one thing that you can see here is this graph with these infinite ends standing out in 3 directions. So this has 3 holes, right? And so these 3 holes that you see on the left-hand side correspond to the 3 holes that you see in the yellow shape on the right-hand side. Also, if you count, as you see these 3 directions in which these rays go off, and in each of these directions we have exactly 4 of these things, and this is exactly the degree of that polynomial that we looked at the beginning. So in tropical geometry, it just says, well, none of this is a coincidence. Okay, so this is what this picture says. But I will be a little bit more specific. So now I'm getting a little bit more formal. So you can look at power series with real coefficients. And so you make some assumption about convergence of these series, but that is a minor thing. So you have power series, let's say, with real coefficients in some parameter t, and the exponents of these expressions in t are arbitrary real numbers. In order to make sense, there are some convergence conditions to be satisfied, but let's sweep this under the rug for now. So what is important is if you look at this set of real power series with real exponents and real coefficients, then it is known that these you have the usual addition of series, you have the convolution product, so then you get a field in this form. So it's the field of Puiseux series or generalized Puiseux series, and it is known that this is a real closed field. So this means in terms of model theory, it just behaves exactly like the real numbers. It's just a funny way to write down the real numbers. So that's one way to see that. Okay, so what can you do with this? Well, the interesting thing is with this field, it admits a special map. So this is this map ORD, and it just takes such a power series, and so the degrees, so the exponents in this power series are ascending, strictly ascending. And so and they begin somewhere. So there's always a lowest exponent, and this map ORD, so the valuation map, takes such a power series and assigns it the lowest exponent. Sorry. In this version of the talk, so there's always an ascending and a descending version. In my version of this talk, because it fits the optimization pattern, so the exponents are descending. Sorry. Yeah, so it is, but the valuation map assigns the series its first, the exponent of the first term, and this is the highest order term. And so in this example, it's alpha 1. And then you observe that if you multiply 2 series, then the valuation of the product is the sum of the 2 valuations of the individual factors. And if you play the same game with the addition, so then you get an inequality. So where the valuation map takes a sum and maps, and the result is less than or equal to the maximum of the valuations of the 2 summands. And so this is in general a strict inequality because there can occur consolation. But if we look at real coefficients, then okay. So I was talking about this valuation map, which assigns a real Purseur series. It's the exponent of the highest order term. So there's a hand raised. Do you want to ask a question?
Yeah, Aftab, do you have any question? Aftab, you raised your hand. So do you have any question?
No, that doesn't seem to be the case. So
yeah.
let me continue. So the upshot is this map provides a semi-ring, a semi-ring homomorphism from the semi-ring of positive real Purseur series to the tropical semi-ring that I just defined. And the positivity is decided by the coefficient of the highest order term. Right, so you have the highest order term and it has a coefficient C alpha 1, and if this is positive, then the entire series is called positive. And yeah, so these are the properties that we have. Now we are going to use this to define a process which is tropicalization. So this is now the formal description of what was going on to go from the yellow picture to the piecewise linear picture that I showed you before. So just imagine you have a polynomial in d variables, right? So these are the variables x1 up to xd with some exponents, and the coefficients are these real Purseur series, right? So gamma tau is one coefficient, delta t is another one. And now we want to define the tropicalization of these polynomials. Well, we do this as follows, and with coefficients in this field that I described, this field of generalized Purseur series. And the process that I do is I write down something which looks formally very similar, but I take the coefficient, which is this real Purseur series, I map it to its valuation, and then I take the monomials just as they are, but for the purpose of evaluation, I'm using the arithmetic of the tropical semi-ring. So that's why I'm writing this as this. Let's do this as for an example. So now I'm just taking a univariate polynomial in one variable x, and then so it is a degree 3 polynomial in x, and the leading coefficient is 1, and then the second coefficient is t to the third plus 2 to the t plus 1, and so on. So now I'm tropicalizing this term-wise. Then, for instance, so here the leading coefficient 1, so gets mapped to 0. So this is 0 plus x to the third. And here the 3 get maps to 3, is 3 plus x to the second, and so on. So I get 4 original terms, 4 new terms. And if I translate the tropical arithmetic back into the original arithmetic with max and plus, so then the evaluation map of the capital F tropical polynomial is the maximization of 4 terms, 1 for each term of the original polynomial. And so all of these are linear functions which are in x, which I'm optimizing over. And this is why you are seeing these piecewise linear pictures. All right, so this is this tropicalization process explained for this one polynomial. And what's the result? So there's a main theorem due to Kapranov who says if you have a polynomial over a complex Purseur series in d variables, then the tropical hypersurface that is assigned to the tropicalization, so this will be explained in a minute, this coincides with the pointwise evaluation, pointwise and coordinate-wise evaluation of the valuation map to the vanishing locus of this polynomial. And there's a more general version to this for arbitrary varieties, but that's less important for now. We just use it for hypersurfaces. Now we only need to know what this T of F is. So that is the tropical vanishing locus. And it turns out, well, so the tropical polynomial is a maximum over several linear terms. And that tropical polynomial is defined to vanish if that maximum is attained at least twice. And then if you apply this to this curve, to this elliptic curve that I showed you before, then you get exactly this picture. So this is Kapranov's theorem, which is behind all of this. So this relates classical algebraic geometry over a slightly funny field, but which is, so CT is an algebraically closed field of characteristic 0. So it is, from model theory terms, as good as the complex numbers. And then, so this valuation map structure allows you to relate this to this piecewise linear geometry in this way that I explained. And again, so here's this univariate polynomial that we saw on the previous slide. If you do the math, you find out the original polynomial, for instance, vanishes at x equals 2 times t. And then the tropical polynomial, which is on the bottom line, so this is the maximum over these 4 terms. So this vanishes at the valuation of 2 times t. So 2 times t is 2 times t to the 1. Therefore, the valuation is 1. So it's the exponent of this thing. And you see the max, if you plug in 1, so then the first term is 3 times 1 is 3. Second term is 3 plus 2 times 1 is 5. The third term is 4 plus 1 is 5. And the last one is 4. So the maximum is 5, and that maximum is attained twice. And that is why 1 is in the set T of F for this particular polynomial. So that's the mechanics, what is behind this tropicalization procedure. Now we need to figure out how is this related to optimization. And here's a problem that's from the real world. So I guess, so I heard that in Pakistan, people like cricket. So just imagine you're a coach of a cricket team, a very small one with only 4 players, and you have 4 positions to fill. And now you want to find out, so who's supposed to play on which position. And you do a lot of training and you take scores, and let's say, so you this way you produce a matrix. So that's this matrix. Let's say the players are the columns and the positions are the rows, and you just measure how well each player plays on each on each position, and then you want to find the optimal team, right? So this is known as the linear assignment problem. And if you write it down, so then an assignment is a choice of these coefficients, 1 per row and per column. And so, of course, these correspond to the permutations of the columns or the rows. So if you have 4 rows and 4 columns, so there are 4 factorial 24 of them. And for each, you can measure the total strength of the team, right? So and for instance, if the assignment that you pick, so player 1 plays on position 1, player 2 plays on position 2, so then the total value of the team, if they play on these positions, is 2 plus 2 plus 2 plus 2 is 8, right? And in this particular case, that's the best choice that you have for these people for these petitions. And if you spell it out as a formula in a naive way, so then you're computing the maximum over these 24 permutations, and you pick the corresponding coefficients, and you sum up their values. Now, if you translate this into the tropical, into this tropical arithmetic, it looks like this. That's not very impressive. But if you think about it for a short moment, so this is exactly the tropicalization of the classical determinant formula, right? So this is like this formula for the determinant. There's a sign in the classical formula, which is +1 or -1 for each term. So what they have in common, their valuation is both 0, so this goes away. And so what you see here is that the linear assignment problem just comes about naturally in the tropical setup by tropicalizing the multivariate polynomial given by the determinant of a matrix. Okay, so here you see that there are natural optimization problems which actually happen and are important in the real world, which are naturally linked to this version of tropicalization. So that is that is the end of my introduction into this topic, and then I will go to more specific things. Is there a question?
Yeah, Professor, this is a completely tropicalization of the classical simplex method of linear transformation. Sorry.
So I didn't talk about the simplex method yet. So this is really only a determinant. So there's no no linear programming yet. So this is just the classical determinant as a multivariate polynomial tropicalized, and this leads to a classical problem. So this is known since the 1960s. What I'm telling you now.
Okay. Thank you.
Okay, so there's what I should say is, so this is just the tip of the iceberg. So there is a large number of optimization problems which have been related to tropical geometry in this way. There's a vastly incomplete list of references. There are a number of textbooks, and so I happen to be an author of a more recent version of this. Yeah, where you can look up more stuff along these lines. So there's another question.
Yeah, by Vakas.
Yes. So I have a very basic question. Are there many changes if we change the semi-ring structure from by defining the addition using the minimum instead of maximum?
No, not at all. I mean, so you get exactly the same, but everything is just upside down, right? It is essentially a matter of taste, and actually if you start out with real algebraic geometry where people know these Puiseux series, for them it would be more natural to have increasing series of exponents. Then you map to the lowest order term, and then you end up with a minimum. So that is totally natural. The reason why I picked the maximum and a slight non-standard version of the Puiseux series is this makes it a little bit easier if you want to do optimization, because if you do minimum tropicalization, then the valuation map reverses the ordering, and then it's just a little bit, it's inconvenient to read. But there's no difference.
And the theory exists for formal power series too?
Yeah. So there's formal power series conversion. There's a whole zoo of power series that you can consider.
Okay.
Yeah. In my book, I have a chapter on the various choices that you have. Okay. All right. So, and then here's this little bit of a tropical dictionary which relates optimization problem to things which exist in tropical geometry. And this introduction was just the first line of this dictionary. Let me move on to my actual topic. So now I want to use these tricks to study linear programming. So what is linear programming about? So that's an optimization problem which comes about from three data items: a matrix A, and a column vector, and a vector B, and another vector C. So I want to minimize C times X, so subject to the condition that A times X is less than or equal to B. So the last inequality is so if A is a matrix and X is a column vector, right? So then A times X is another column vector, and then this inequality is meant to hold for coefficient by coefficient. Okay, so we want to find a minimum X such that C times minimum an X such that C times X is minimal subject to the condition AX equals to B, and the conditions define in general unbounded polyhedron. Here it is this bounded example in my picture cartoon. It's a pentagon, and so the points of equal value with respect to the objection function. So these are parallel hyperplanes, and so these are so each hyperplane is in purple here, and there's an optimal hyperplane which just touches this polytope, and so the optimal solution in this example is unique. So this is just this one vertex of this pentagon. Okay, now there are a number of algorithms to solve linear optimization problems, and I will sketch two algorithms. So the first one historically is the simplex method, or one, yeah, there are predecessors like always in mathematics. But so Danzig in 1947 said, okay, So let's start at an arbitrary vertex of the feasible domain, and let's ignore for now how we get there. Okay, so that is a different problem, but it's kind of easy. We start at a vertex, and then we take edges in the of the polyhedron, which defines the feasible region, and to optimize, to move from one vertex to a better vertex until we cannot improve it any further. So this is what the simplex method does. And so there's various ways to characterize when we reach the optimum. And the most important characterization goes to linear programming duality, for people who know how this works. Okay. And so this is a method which depends on a pivoting strategy, which means you need to decide how you want to move from one vertex to the next, if there are more than one improving directions, which in general is the case. All right, so this is the simplex method, and there's another method, which is the interior point method. The basic idea is due to John von Neumann, and it became particularly popular in 1984, where Kamaka proved that there are fast algorithms that you can produce in this way. So it's kind of similar, but also different. You start as a specific point of the feasible region. This time it is not a vertex, but it's a kind of in the middle. It is known as the analytic center. And then you just trace a certain small...
Come on.
Sorry, was there a question? Okay, so
no question, some mic was on.
I see.
Yeah.
Okay, so and then via some auxiliary non-linear optimization problems and applying Newton's method, you trace a certain smooth curve toward the optimum. So that is what so because you go through the interior of the feasible region, this is known as the interior point method. And again, you can characterize the optimality. So this is slightly more general than only linear programming. And so the main result due to Kamaka is, so this is a weakly polynomial time algorithm. So it's a polynomial time algorithm measured in the input size of the system. So the linear programming is defined by the matrix A and the two vectors B and C. They have encoding, so think these are rational, and they have encoding lengths in bit patterns, and then you measure how large this is, how many bits you need. And so then the complexity of this algorithm is weakly polynomial in the bit size of these systems. So the simplex method depended on this pivoting strategy, and this depends on the barrier function, so which defines these auxiliary optimization problems that I mentioned. Okay, so that is a very crude overview over these methods. And in the literature, it was known. So the question is, how fast is linear programming? If you want to be more precise than only talking about weakly polynomial time. So the question is there a strongly polynomial time algorithm? I will explain this in a bit. So this is a question which was made prominent by Steve Smale in a celebrated paper written in 2000. So this is a list of problems for the 21st century. So Smale set up a list of problems that he deemed most important for the mathematics of the 21st century. And the original statement is slightly more technical, and I'm paraphrasing only very mildly. So, and then he asked, does there exist a strongly polynomial algorithm to solve the feasibility problem of linear programming? So what's the difference between weakly polynomial and strongly polynomial? Well, so I'm taking a shortcut here. So remember, the input of the linear program are the matrix A and the vectors B and C. And for a weakly polynomial, we measure the size as the bit length of all the coefficients of these three things combined. So that's the encoding length of this thing in the bit model. Now, this matrix has a number of rows and a number of columns, so M and N. and then the vector b, if m is the number of rows, then the vector b is of length m, and then the objective function c is of length n, the number of columns of the matrix A. And then the question is, does there exist an algorithm for solving linear programs such that the running time is polynomial in these parameters m and n? So that's the question translated into plain English. And this is what Smail considered a major open problem for mathematics. So what is known is, so Kamakar proved that the interior point method is weakly polynomial. Previously, Kachian showed that a different algorithm that I don't want to explain now is also weakly polynomial. There was a result by Borgward that the simplex method is even strongly polynomial for on the average in a certain sense, but not in the worst case, and we are interested in the worst case complexity. And so there is a version of the simplex algorithm, so there's a special pivoting strategy which is randomized and which shows, well, it is better than exponential, but not polynomial. So it is known, so for the simplex method, no polynomial time pivoting strategy is known. And and for the interior point method, no strongly polynomial barrier function is known. And now this is now the more exact version of my main result that I mentioned in the beginning. So there's a family of linear programs which depend on two parameters, r and t, but they are of a very different nature. So LW for long and winding. So there's a family of linear programs in 2 times r many variables with 3 times r plus 1 constraints, which depend on a real number t, which is larger than 1, such that the number of iterations of a large class of reasonable interior point algorithms with a log barrier function is exponential in that parameter r, provided that the t is large enough. Okay, so there are a couple of gaps in this statement because, as usual, for negative complexity statements, the details are a little bit intricate. And so I will say a word about this in a second. But before I do this, so there's another more geometrical result, which concerns the same family of linear programs. And you saw for the interior point method in my cartoon that there was this curve from the analytic center, the smooth curve from the analytic center to the optimum. This is known as the central path. And the total curvature of this path is also exponential in this parameter r. So this is a related result, but so there is no direct path from one result to the other. It just happens so that for this particular class of linear programs, we can prove both things. And now here are the more technical details. So we are talking about primal dual path following interior point methods with the log barrier function, which iterates in the wide neighborhood. But this is it's technical, but this is it's a reasonable assumption. So you should think a large natural class of linear programming algorithms. And and this is exponential in this parameter r, and the parameter r dictates the number of variables and constraints. And so this means these algorithms cannot be strongly polynomial on this family of linear programs. This is the main result that I want to bring across. So the proof is a little bit longish, but it substantially relies on tropical geometry, and I want to bring across the main idea. Okay, so let's first look at these linear programs, how they look like. So as you saw, so they depend on two parameters, r and t, and r just dictates the size of the linear program, and the t does something that you didn't see yet, right? And so the t occurs in the coefficients of the linear program. So what you see here is the full version of this class of this family of linear programs. So the optimization function is very easy. You just maximize the first coordinate. So the coordinates are x1 up to x sub 3r plus 1. Sorry, up to x sub 2 times r. And so we have 3 times r plus 1 many constraints. And you can see this, for instance, the first variable is less than or equal to t squared. The second variable is less than or equal to t. And then there is kind of a little bit of a recursive pattern in the sense that you see some variables on the left-hand side which are constrained by terms in the previous variables. And then there are among the coefficients, you see this additional parameter t occurring as a coefficient, sometimes powers of t, as coefficients to the variables that we have. And then there are 2 non-negativity constraints, and if you count the number of constraints, you add up to 3 times r plus 1. I should say, so the entire feasible set is contained in the positive orthant, so all variables are non-negative, but so what you see here is a facet description. So the non-negativity constraints for the other variables are implied by the conditions that you see here, and only for the 2 last variables, these are facet defining, so these are non-redundant. And now I'm looking at this family of linear programs which depend on R and T. And if the T is very large, so then these central paths are very curved, and this goes together with the fact that optimization via the interior point method takes a long time. So concerning the time of this talk, so how do we deal with this Zoom bombing thing? So for how long should I speak now?
Oh, okay, you can continue, Professor Joswig. It maybe 5 past 10.
Okay, I'll be quick. Okay, so this is this very class of linear programs. And so you see here, so the inequalities that you see should look familiar if you go back to the first part of the talk, right? So these are essentially polynomials in these x's with these powers of t adorned. And and then these are terms which are amenable to this tropicalization, and that's the whole trick. But it's not obvious what you gain from this. Okay, so now here's the setup. You have this data which define your linear programming: matrix A, right hand side B, objective function C. Then you have this linear programming. We minimize C times X subject to AX less than or equal to B. And here I want to have, I'm assuming I have non-negativity, right? So then there is a dual. I mentioned a linear program duality. So it's a mechanism to define another linear program from the same data. So, but instead of minimizing over C, now I'm maximizing over minus B, and my conditions are a little bit changed too. So I'm looking at the negative transpose of my matrix A, and kind of the B and the C, the right hand side, and the objective function up to sign switch their roles. So that is and then the main result of linear programming just says, well, the optimum under mild conditions, the optimum of both optimization problems is the same. Okay, and now in this setup, I can cook up the logarithmic barrier problem, which just looks like this. Right, so this is the auxiliary problem which defines the smooth curve for the interior point method. So this this looks at the feasible constraints as before. Instead of ax less than or equal to b, we spell this out as ax plus w equals b. So these are slack variables where the w's are required to be non-negative. I'm writing strict positive here for a reason. So, but as a linear program, this would be just x greater or equal to 0 and w greater or equal to 0. And and instead of minimizing just the objective function, I rescale by a new parameter mu, and I subtract the log values of the x's and the w's, of the original variables and the slack variables. And now, so this is a problem, another optimization problem, which depends on this parameter mu. And if the parameter is very small, so close to 0, right? So then this term dominates the other terms which do not depend on mu. So this means for mu very close to 0, I'm essentially minimizing, I'm solving the same as the linear optimization problem. But when I make the mu very, very large, so then the term in the beginning does not play a big role, and instead these logarithmic terms dominate this expression. And then this is how I define the analytic center of this thing. So that is a very nicely behaved optimization problem that I can solve easily via Newton's method. Okay, so this is how I go from a linear program to its dual and the associated logarithmic barrier problem. Now, the key thing is that linear programming duality translates into these conditions which are given now in terms of simultaneous equalities for the primal and the dual linear program with slack variables w and s respectively, and then these conditions for the parameter mu. Right, so these are linear conditions, and these are quadratic conditions in the combined variables w and y, which fix the parameter mu. So linear programming duality translates into the fact that for given mu, so there are unique, under mild conditions, there are unique solution vectors y depending on mu and s depending on mu, such that the vector that we get from putting together the primal variables, the dual variables, the primal slack and the dual slack, that this is the unique solution to this non-linear set of equations and inequalities. And so this mu is an explicit parameterization of the central path. Okay, and so the goal is to start with a large value of mu and to drive it down to 0, large positive value to this parameterizes this special curve, and tracing this curve is what the interior point method does. Okay, that's the cartoon for this. Now, let's look at an easy example. Right, so I told you so that the real Puiseux series that we looked at before form a real closed field, which means we can do linear programming over them. And here's a toy example, right? So this is feasible. This is a polyhedron which is given by two variables x and y, subject to 1, 2, 3, 4 conditions and non-negativity conditions. And the coefficients sometimes involve this parameter t, which occurs in these formal or convergent power series. And now it just looks like the individual terms look like these polynomials that we saw before. And those we can tropicalize. If we do that, then x plus x2 becomes the maximum of x1 and x2. Then the 2 becomes the valuation of 2. So 2 is 2 times t to the 0. So therefore we have 0 on the right-hand side. Similarly, here we have t to the 1, which becomes 1 plus x1, and similarly for the other terms. So that's a tropicalization of this linear program, and this works since we are in the positive orthant. And then due to the fact that if we restrict to positive real Purseur series, then the valuation map works like a homomorphism of semi-rings. Okay, so and then this is a mechanical way to pass from a feasible region of a linear program over Purseur series to inequalities in this tropical arithmetic, and the feasible set is a tropical polyhedron. Again, piecewise linear because we look at maxima of linear functions. Okay, so how should you think about this? Well, so think about this in this form. So this is a cartoon on the left hand side, so which refers to the previous example. So we had 1, 2, 3, 4, 5, 6 constraints, right? So and here we have and one of them is not binding, so one of them is redundant. So we have 5 non-redundant constraints, which cut out something which looks like this. Okay, but now it lives over Purseur series. But we can sorry, yeah. So we can look at this linear program that we saw here also for a fixed value of t. Sorry, we can look at the fixed value of t, and then it just looks like an ordinary linear programming like this. And then we can deform it by applying the map which sends x to the logarithm of x to the base t. Then it maybe looks a little bit like this, a little bit rounded. And if we drive the limit, if we drive this logarithm to the limit by setting t to larger and larger values, so we take the limit for t to infinity, it can be shown that this always exists. Then it just looks like this. So this is the tropical linear program. So this logarithmic deformation, which is also known as Maslov dequantization in functional analysis, this is the method which sends a linear program to a tropical linear program. And then you can exploit this to the relationship between these to study one through the other. And so if you do this and apply this to the setup that we saw, so the key idea is you have the interior point method that is defined by the central path, the smooth curve, built through these auxiliary optimization problems. They are known to be characterized by these polynomial constraints. You tropicalize everything, and then you can apply the machinery that I explained to you. So you get the tropical central path as the point-wise and coordinate-wise image of the central path over Purseur series under the valuation map. And then this is how it looks like in this case. So for the example that you just saw before, depending on which optimization function you want to optimize, so the analytic center is always at the upper right. And then if you want to minimize x1, so then this red curve going along the boundary is the central path. If you want to minimize t times x1 plus x2, then you go a little bit along the boundary, but in the other direction, and then you go through the interior. So this tropical central path is the key geometric player to study the complexity of this class of algorithms, and also the relevant for studying the curvature of this thing. Okay, so summing up, we saw that tropical geometry is useful for getting insight about details in linear optimization. So please recall the original statement that I wanted to explain does not mention tropical geometry at all. It is just it's a statement about the simplex method in general, and it just sheds new light on this on this method. There's another. So this is in the second paper that is listed here. So what I reported on. There's another paper we also worked on the simplex method that was before, but that's for another day. I should also say I stressed the point that yes, there are some technical requirements for the statement on this interior point method, but since then, two of my co-authors with another young guy, Van Dam, they generalize it further to a larger class of interior point methods. So, and that's a fairly new result from last year. Okay, thank you so much for your attention, and I'm open to answer any questions that you might have. Thank you.
Thank you, Professor. Are there any questions or comments from the audience about? Okay, Professor, where do this log barrier interior point technique arises in general in simplex method?
In the simplex method, it does not arise at all. But so if you do interior point methods, that is like the most natural thing to do. That is really, this is like if you open up a book on linear optimization, which discusses the interior point method, that's the first example.
And how log? Oh, okay. So minimizing this particular. And what's the role of logarithm in getting into the business of the interior point? I just missed that particular part.
Well, so so why this particular function is used for linear programming? Yeah. So okay. So the logarithm function. I mean, if I write it like this, so you see it's a convex function, right? And so if you everything depends on the parameter mu. And if the parameter mu is large, so then the leading term, so then the leading term almost vanishes. And then you get a smooth optimization problem, which is convex, that you can easily solve via Newton's method. So that is you should think, okay, so linear programming is not the most complex optimization problem that you can imagine. But in this world, for describing how this method works, you should think of, you want to try to solve a large linear program. Therefore, you do it in a step-by-step fashion. You create auxiliary optimization problems, and this is much easier than solving the linear program.
Yeah, because a general impression which this function gave, why not one apply the Lagrange multiplier methods in order to deal with this? We have a parallel method in order to minimizing a particular system subject to the linear condition.
Yeah. I mean, there are many ways to solve linear programs. I mean, many more than only the simplex and the interior point methods. But so there are two aspects to these methods. So first of all, theoretical, and you're right. So Lagrange methods would be suitable as well. But then there are also practical concerns. And for practical concerns, if you implement that and you want to actually do this in practice, and we are talking about linear programs with millions of rows and millions of variables, then there are only two things left. And this is either the simplex method or the interior point methods. Nothing else can compete. Okay? At this point, Lagrange is out of the business.
And I would like to see those diagram once again, where you were showing the feasible region. The next slide.
This one?
Yeah, this one. Yeah. So I didn't get that with the logarithm how it affects the shape. So it affects the shape of all the boundary.
Well, of the boundary of the feasible region of everything. Okay, so okay, let's go back to this thing here. So this is a description. This is a description in terms of these Puiseux series. Okay. Right? And so what is really important is we assume that the variables are non-negative. Everything is restricted to the positive orthant. Okay, And now I have a mechanical process of turning this into this thing by tropicalizing term by term.
Yeah.
Now what I'm saying is, so for a short moment, imagine T would be a fixed real number, let's say large, let's say 16, okay?
Okay.
So then the feasible region looks like this.
Mm-hmm.
Okay, and now I'm changing. And now I'm taking this set and this gray set
Mm-hmm.
and apply point and coordinate-wise logarithm with base 16.
Okay. 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 Okay.
Right. So this is the picture. Now I was
Oh, okay.
right. So then so here everything is in the positive orthant. If I take the logarithm from 0, I arrive at infinity, right? So minus infinity, and therefore, so this is unbounded here in this direction.
Mm-hmm.
But doesn't disturb me. So it's this is how it happens in this case. It could also be bounded in this case, but this doesn't. But it's not a problem.
But
And now,
how? Yeah, the third picture is the more confusing.
so the third picture. So I told you you can look at this game for any fixed value of t, right?
Mm-hmm.
And then you can take the logarithm with respect to t. So these are the first two pictures.
Mm-hmm.
Now I change my t, right? So you get for each t, you get a pair of pictures on the left and a pair of pictures on the right. Now
Okay.
I want to tell you how the pictures in the middle change if you make the t larger and larger and larger. And in the limit, you get the shape on the right hand side.
It does not affect the brown line, but how?
So the black line.
the brown
this
line.
one.
Yeah.
No, a very good question. So this is comes from, so the brown line is the first inequality, which doesn't involve the t. It just it just happens so in this case.
Mm-hmm.
Just because I picked a particularly boring inequality to be my first inequality.
Okay. And how this green turn into this? Yeah. Okay.
And now I need to guess which one is which. I guess x plus y. Yeah, I should. Yeah, I think. Yeah, so I think it's the last one, x1 less than or equal to t squared, right? So times x2, and then this is the shape that you get.
The green one is the last one, right?
I think so, yes. Yeah, honestly, I didn't pay attention which one was which when I put together the pictures. Yeah, but it's an honest picture in the sense that it really refers to this particular example. And the thing is, the main upshot here is I have a mechanical process to go from these Puiseux polyhedron, so to this from inequality to inequality over Puiseux series and in the tropical world. And this is the same as doing this logarithmic deformation of the constraints. This is a version of this Caprano fundamental theorem over ordered fields.
Okay, thank you, Professor, for attending my queries, and it was really interesting. I never came across a logarithmic barrier, and particularly never seen these things before. This is so interesting. So interesting.
Well, yeah, it depends on where you, so if you do linear programming, depending on your background, so then sometimes for some people it is more natural to play with to go through the simplex method, and for other people it is more natural to go through the interior point method. But both are totally valuable, and they have similar. So you might think that these are very, very, very different. But actually, what also comes out of this line of research that I was presenting, if you look at this example, so in the tropical sense, so you can end up at the boundary, even if you meant to go through the interior, which means if for these linear programs that we showed you, so the central path can become arbitrarily close to the boundary, so before this our result, wisdom in my smooth optimization friend community was, well, the interior point method is superior to the simplex method because it avoids the intricacies of the combinatorics of stupid polytopes, right? And so, but what these examples show, it's not true. So the central path can be forced so close to the boundary that it suffers exactly from the same problem with the combinatorics, even if you don't see it right away in your equations.
Yeah, literally, and this is something which is quite clear from the left side due to the binary operation of the tropical one, but on the right side, I think with the ingredient of tx1 plus x2.
Yeah, so this just explains so that various scenarios are possible. So, but so of course I was talking about worst case complexity, right? And so for our things for this family, I gave you a specific set of constraints, but also a specific objective function, right? So. And then for this objective function, for these constraints, so this is what happens. So this is you're forced very close to the boundary, and then for the central path, and then you suffer from these degenerations.
And it is possible that both the methods are going to give us the same optimization value on the boundary.
Yes, I mean, so yeah, so you mean the simplex and the interior point method? Yes, so yeah. This is always the case. But so what this analysis does is it can happen sometimes that essentially the simplex method and the interior point method essentially agree, right? So you have a path in the boundary by the simplex method, and then the central path is so close, it is in the interior, but just barely. So it is so close to this vertex edge path that you're following that is essentially the same. And in the tropicalization, you don't see a difference anymore. Because by passing to the limit, well, then that guy just is on the boundary, on the nose, end of story.
Okay. Thank you, Professor. Thank you very much. Are there some comments from anyone or any questions? Okay, I think we are really very thankful, Professor Joswig, for this wonderful talk. I'm extremely sorry with the audience and with you for the inconveniences in the beginning of this particular seminar. We will share the recording with you, Michael, so you can put it anywhere. Share with your in your circle as well.
I will put it on a link on my webpage, if I may.
Okay. Thank you, everyone. Thank you very much. Thank you, Professor Joswig.
Thank you for having me.
Thank you. Bye-bye. Take care.
Bye.